All right, everyone. Today's seminar live stream, we have Francesco Chiariello, and he'll be talking about declarative process specifications, reasoning and mining temporal formula. All right, so Francesco, welcome, and go ahead.
Thanks for the introduction. Okay. Hi, everyone. I'm Francesco Chiariello from the Artificial and Natural Intelligence Toulouse Institute in France, and I'm going to talk about declarative process mining. So, okay, we will start with a brief introduction about what is process mining, what is temporal logic, and then we see how we can specify models declaratively using a linear temporal logic. So we will introduce temporal logic and process mining. Then we see process mining, that is the combination of the two. In particular, we will use linear temporal logic to specify the models. And then we will introduce some process-related tasks, such as log generation and conformance checking, trace alignment, process discovery, and process repair. And we will see how to model them logically to solve them in an automatic way. So, first of all, what is process mining in a nutshell? Here, I have reported a definition of process mining. Process mining is about analyzing event logs to discover, monitor, and optimize processes by deriving or enhancing process models. So I have highlighted in bold the three main ingredients of process mining. We have processes that generate event data recorded by the event log, and the processes are represented in some formalism using some process model. So we have an ongoing process here that is generating traces. Those traces are recorded here. Then we can use those data, those event data, to improve the model of the process or to learn a model from scratch. To make things more concrete, here I have reported a model of a process. Here is in a business process model and notation, but it's not important to be familiar with the formula. So here we are modeling how the process of producing and consuming a pizza. So we start by buying the ingredients, then we create the base of the pizza, then we add the ingredient on the pizza in any order. So this plus sign here, the parallel gateway indicates parallelism. After that, we bake the pizza in oven, we eat the pizza, and then we clean the kitchen. So here in this particular case, with this model, we have 3 factorial different process traces, where a process traces, or sometimes simply called a trace, is a sequence of activities from start to end. An event log is then a collection of those traces, a multi-set of traces. So each possible trace will have a multiplicity representing how many times it occurs in the event log. Here we can see how an event log looks like. Pardon? So every row here is a record of an event. We see the activity being performed associated with the timestamp in which the event occurred, the resource performing the activity, and here in this particular case, we have a customer requiring the pizza. Then the pizza are also associated to different cases, so that processes may actually be executed in parallel. We can execute in parallel different instances of a process. But since we have an ID to identify for each activity to which trace it occurs, at the end we can think of them as a multi-set of traces, as I said before. So now we can introduce the process mining task. Conformal checking is the process of verifying whether the traces of a log are compliant with a process model. So whether the traces could have been generated by the model of the process we have. Log generation instead is the problem of generating the traces of a log, is to generate a certain number of traces starting from a process model. And this is used for testing and analyzing to better understand the behavior of the model we have. Then, if the traces are not compliant with the model, we can ask, how can we modify the trace to make them compliant with the model? And this is the task of trace alignment. Then process discovery is the task of learning a model, of discovering a model, starting from the event logs only. Process model repair, instead, we have already one model that does not perfectly match with the traces, and we ask how to modify the model in order to make it compliant to the data. So while in trace alignment, we modify the trace to make them compliant with the model, in process model repair, we assume the traces to be correct, and then we modify the model. I think everything will be clear after we introduce the notation. But if you want to ask something.
Yeah, so can you go over what a trace is again?
What is a trace?
Mm-hmm.
A trace is a sequence of activities. So buy ingredient, create base, add cheese, add salami, add tomato, bake in oven, eat pizza, clean kitchen. That is one trace.
Mm-hmm. Okay.
In this particular case, any possible linearization of this model represent a trace.
And the plus means that those things can be executed in parallel.
Yeah, any permutation of those will result in a trace.
I see. So there'd be a different process if we wanted to make sure that we added the cheese first, let's say.
In this case, for how we model this process does not matter. All of them are equivalent.
Mm-hmm.
All of them belong to the same process.
Right. Okay.
Okay. Let's now introduce temporal logic. Linear temporal logic over process trace is a formalism for specifying the properties of the traces of a process, and so of the corresponding process generating the traces. Therefore, linear temporal logic will allow us to reason over the sequence of activities performed by a process. And it is a modal logic having a temporal operator like next, until, eventually, and globally, whose semantics will be introduced shortly. So first of all, the syntax. Given a set of propositional symbols, which in our case will correspond to the set of activities that can be performed by the process, the syntax for generating well-formed formulas is as follows. So if A is a propositional symbol, if A is an activity, then A is a well-formed formula. The negation of a formula is a formula. The conjunction of two formulae is a formula. The next of a formula is a formula. Phi1 until Phi2, where Phi1 and Phi2 are formula, is yet another formula. And then we can, here we assume only next and until as temporal operator in the syntax. And then we see that we can define other temporal operator in terms of those other operators. One can define, first of all, the Boolean connectives. Then one can define the eventually a formula, globally a formula phi, a weak next of a formula, and the weak until. Let's
wait.
now
what
better
was F
understand.
again?
Pardon? Eventually. We will introduce the semantics here. So we say, given a trace P, which is T1, and an instant, in a time instant, represented in green, yeah, we say that the formula next phi is true in the time instant E if phi is true in the next instant I plus 1. The formula phi1 until phi2 is true in the instant I if eventually phi2 holds at some instant j greater or equal to 10e, and for all those instants until that instant j included, phi1 also hold. Eventually phi hold in a time instant I if phi holds at some future point of the trace, here j, pardon. Globally phi or always phi is true at time instant I if phi is true in all the instant from now on until the end of the trace. Here we can introduce formally the semantics of linear temporal logic. So given a formula and a trace, which is a non-empty string, a time instant from 1 until the end of the string, the semantic is defined as here. A is true in an instant if A is the activity performed in that instant, the base case. The negation of a formula is true if it is not true, the formula, here should be only phi. If the formula is not true, the negation is true.
Wait a
The
minute.
conjunction.
Hold on. So the first one, that's saying that you have a process and a time integer step number. And if we say that A, if and only that at the wait, what, okay, so
A is an activity, so it's the base case.
And
we have a string which is
the process at time I is A if and only if A equals the only thing at that time slice.
Yeah.
Okay.
Exactly.
But in general, there can be more than one things going on at a time.
No, actually, we assume one activity to be performed at every time. So why the action could actually be durative, we will just order them according to when they finish. So we can assume to have only one activity performed at any instant. Therefore, we have just a string over the set of activities. This is what a process trace is.
And so the things that run in parallel, I guess, you know, if
in parallel means that any possible linearization of them that could be a valid trace, but in the practice we will observe one of them.
Okay, so
or one.
It's like a race condition, because if you have all these separate threads doing different activities, then in general only one of them will finish at a time. Like they won't finish at the same instant. Or if they do, it'll be like sequenced at
the connection.
Oh, yeah, the connection might have cut out.
Yeah, maybe we can go back to asking a question again later. I've got a feeling it's going to get a lot more complicated before it gets understandable again here. This is quite an advanced topic. Cool.
Okay. All right. So yeah, the trace is one activity at a time. Got it.
Yeah.
Just not sure what this conjunction is. Does it mean there are two activities at an instant?
Those are formulas, so you can define a formula recursively. For example, let's go back here. We say that next phi is true at time instant I if the formula phi is true at the next instant I plus 1. But that could be another composite formula. So it could be phi could be next psi, which is true if psi is true at the next instant, I plus 1. But you can notice that to evaluate a formula, we are actually going to evaluate sub-formulas, which are shorter. So at some point, we reach the base case, which is to verify which activity is true at which point.
Okay, good. So basically activities are also decomposable into, each formula is decomposable into usual sub-formulas or whatever.
Formulas built from that. So we start from
Yeah.
activities and we construct by applying next operators to the activities, until operator and doing the conjunction, things like that.
So
Obtaining
activities is like a
formula.
terminal formula, right?
Activity is like a proposition.
Like a terminal here in that type that you have there. It's a
No,
leaf,
can be
like true or something else.
not necessarily the last instant. We talked using the temporal operators about different instants. And then we can ask which activity is true in which instant. Maybe we can see some example later of a temporal formula will be a little bit clear.
All right, okay, thanks. Let's see.
So this is the semantics, but I think we can skip. So we have defined, we can skip the detail. We have defined what does it mean for formula to be true at a certain instant I of the trace. Then we say that the formula is true with respect to the trace if it is true in the first instant of the trace. A theorem holds that say for each formula phi over sigma, there exists a finite state automaton over sigma such that the finite state automaton accepts exactly the traces that satisfy the formula. Here we can see a first example of a temporal formula. The formula says globally, if A, then eventually B, which means that for all time instant of the trace, if we see the activity A, then we must eventually see B as well. And we see here the corresponding automaton. So we start from the initial state S0. If we see at some point the activity A, we move to S1. And in a sense, we have activated the constraint. What we want is to eventually see B. So we stay in S1 until as long as we read A or any other symbol other than A and B. This is what this C stands for, any other symbol in sigma. When we see B, then we move back to S0, which is also an accepting state. And so we can say that the string, the trace, is a model of the formula, satisfy the formula. Any question here?
So your arrow is the implication, right? It's expressed using not and
Yeah, it's an implication.
it's like you in terms of other logic operators that are in your formula is just not, right? Or not A or FB, right? That's how you write it.
We have basically all the propositional operators. So the and, the implication, we can define the or in terms of the other. And then we have the modal operators. In this case, we see globally and eventually. So to evaluate this one means that at the current distance, we see A. And if we see A, then we look the remaining part of the trace to check whether we see some B. If we see some B, then the traces has this property. Otherwise, it does not.
Mm-hmm.
And the semantics of linear temporal logic is just reduced to read the trace through this automaton and follow the arrow. We start from the initial state of the automaton, which is S0, indicated with this arrow here. If, while following the arc, the transition of the automaton, while we read the trace. If we end up in an accepting state, which is in this case, again, S0, which is indicated with a double circle, that means that the trace is a model of the formula. The trace satisfies the formula. We don't need to, not even to reason about the semantics of the temporal logic. We just have to execute the automaton for reading the input trace.
Is this theorem like a constructive? Can you actually do it for every formula?
Yeah, we can build it.
Okay.
Absolutely. So let's move now to declarative process specification and declarative process mining. We have seen before a procedural model for representing a process, the pizza process, which was explicitly saying which activity can be performed next, given the sequence of activities we have seen so far. So after we buy the ingredient and we prepare the base, the next action is one of adding the ingredients, one of the 3 added ingredients. So in the traditional approach, in the procedural approach for process modeling, the model explicitly represents how to build the traces generated by the model. And then temporal logic is used to check the properties of the traces, and so the processes of the process, the properties of the process. Instead, in the declarative approach, one asks, why do we need that distinction, a procedural model for the process and then a temporal logic for expressing the properties of the process? We can directly use temporal formulae as a model of the process. So a model in the declarative approach will be just a set of temporal formula with the semantics that the traces generated by the process are the one satisfying all the formulae in the model. And so a declarative model specifies what property should a string, a trace, obey to, rather than how the traces should be routed to satisfy the constraint. Declarative process mining then is process mining where the models are declarative. So here we have an intuitive representation of a process. A process is something that separates admissible traces in green from forbidden traces. An imperative model, a procedural model, then describe how to generate those traces. And there is a problem with that, which is that you end up often over-constraining the model, since we have to explicitly define how to build all the traces. Instead, in the declarative approach, you just list the constraint that whole string must obey. And so this is less prone to exclude traces that should be allowed, the classical type 2 error in statistic. As a negative side, you need a bit of expertise to understand temporal logic, and so design model using temporal logic rather than declarative, rather than procedural models, such as we've seen BPMN models before. To simplify the task, a set of templates called declare templates have been introduced. Here we can see a bunch of them. The template init A, where A is any activity, is saying that at the first instant of the trace, the activity A must be executed. Exactly to A is saying that in the trace, there must be 2 occurrences of the activity A specified by the template. And this is how to express that in linear temporal logic. It's quite complicated, but you just need to express the property you want. So do not worry about how ugly those formulas are. Response AB, we have already seen that, is saying that every time we see A, then it must be eventually followed by B. Responded existence AB is saying that if we see A at some point in the trace, then we need to see also B at some point in the trace. Before or after does not matter. And so on and so on. So maybe now it's clear what are the properties that we can express in linear temporal logic.
Yeah.
Now we see how to encode the main ingredient of declarative process mining in logic in order to automatically solve the process mining task we have described before. So we have to represent process traces, temporal formula. Temporal formulae are the corresponding semantics of LTL. So given a trace, here we have AAB. These traces can be encoded with the following fact. A1, A is at the first instant in the trace. A is in the second instant of the trace. B is in the third instant of the trace. This is a prolog-like syntax, but actually we will use a SAT solver to find the solution of the problems. So we have seen how to encode the trace, which is really natural. It's just a set of facts. How to encode a formula. Here, response AB. To encode a formula, we can just represent the corresponding automaton. So we have to specify what is the initial state of the automaton. Here is S0. What are the accepting states of the automaton? Again, here is only S0, which is represented by the double circle. Then we need to express the transition, the arc. Oops. We have a transition from S0 to S1 labeled by A here. A transition from S1 to S0 labeled by B. A transition by S0 to S0 modeled by B, another one by C. And then we have two transitions from S1 to itself labeled by A and C. This is how we represent the automaton as a set of facts, as a set of propositional symbols. And that's it. This will correspond to the formula represented by this automaton. Now, how to encode the semantics? The semantics just reduce to reading a string with an automaton. So at time instant 0, the state of the automaton in which we are is the initial state of the automaton. So S0 we have seen before. And then we say that at t, we are at the state S2 if in the previous instant, t minus 1, we are in a state S1. If we read at time t the activity A, and the activity A labels a transition from S1 to S2. Here we are just saying, we are just updating the state according to the transition that is activated when we read the activity of the automaton. To check for the satisfaction, we compute the last instant of a trace here, and then we check whether at the last instant we are in a state that is accepting. We have seen here how to represent a trace. Sometimes we do not have the trace and we want to guess the traces. So here we are showing how to generate a trace. Given a certain number of time instants, we want a trace of length t. So we say that for each instant t, the cardinality of the set trace at t with A varying among all the possible activities must be equal to 1. So we are saying at each time instant we consider exactly one activity must be performed, and this allows to generate traces. So now, how can we solve the problem we have described before? So first of all, conformance checking is just this problem. Given a process trace and an LTL formula, in the case of declarative specification, of course, we want to determine whether P satisfies the formula phi. How we solve that? We need just to check if the formula phi holds by invoking a SAT solver with the program we have described above and verify whether SAT is true, whether we can derive that this is true. In the case of log generation, instead, we have only the formula and we want to find a set of traces P such that every trace satisfies the formula. So we invoke an all SAT solver to find all the possible solutions, all the possible guess of the traces that results in SAT being true. For process discovery, which is the problem of given an event log, derive a formula phi, such that every trace in the log satisfies the formula. Now what we do is to guess the formula, is to guess the automaton, and then check whether the automaton accepts all the traces in the log. A special case is the one where we use declare template, where instead of deriving a new formula, we just need to check every constraint we have, every pattern in the declare templates against the log to determine whether that constraint is compliant or not with the log. Any questions so far? Okay.
Just want to see more concrete examples, I guess. How do you discover a process from the log?
Yeah, here I have another problem, which is a little bit different, which is trace alignment, which is the problem of aligning with a minimal number of modification a trace in order to produce a new trace that satisfies the formula. So here we have another example. Again, we have the running essay.
We lost Francesco, right?
Because after the last A, we do not see any occurrence of B.
Can you say that again? You cut out for a second.
Okay. We have here the formula, global if A, then eventually B, which says after every occurrence of A, we must eventually see a B. And we have a trace here, A, B, A.
Mm-hmm.
Such trace does not satisfy the formula because of the last instant. It terminates with A, and we do not see any A after it, any B after it.
Right.
So a possibility to align the trace is to remove the last B, producing the new trace AB that satisfies the formula phi. So the problem of trace alignment can be encoded as a cost optimal planning. We have two actions, del and add. Del corresponding to removing an activity at some point in the trace. Add corresponding to insert an activity. And then we also consider a special action sync of cost null to reduce the problem to a sequential decision problem. So again, let's consider again the example. We have the traces ABA, and we want, and this trace is produced by ABA with the following plan: execute sync, then execute del. The problem can be seen as a text cursor moving from left to right and adding activities, performing del like the del key on the keyboard, or moving right with the rect arrow in the keyboard. So we start from here, and we have all the string ABA to read. Meanwhile, we are on the corresponding automaton in the initial state S0. Then we execute the action sync, which means read the activity A. And we move in this new state where the cursor is in between A and B. And we move on the corresponding automaton from S0 to S1. Then the plan says to perform again a sync. The cursor moves here, and we move back here to S0, which is a setting. We want to end up in an accepting state, which will mean the trace we have generated satisfy the formula. And to do that, we just delete the next A while we stay here. And so the trace generated while we move from left to right is satisfying the formula. Globally, if A, then eventually.
That again.
Solver that support cost actions. We need cost action because the sync action does not perform any modification and so has cost 0, while the add and delete action have cost 1. So this is how the encoding of the actions look like in PDDL, but we do not really need to go over the details. So at some point we are with the cursor at position T1. And when we read activity E, we just move to the next position T2, while we move also on the automaton, according to the transition defined from the current state S1 to the state S2 that is reached by the label indicated by the activities we are reading. So basically, when we perform syncs, we move both on the trace and on the automaton. Here we see add and delete. The add of an activities instead correspond just to a movement, a move over the automaton. So we are in a state S1, we add an activity E, and we move to S2, according to the transition S1, E, S2. Here we see that in PDDL, we also need to say that after performing the activities, we are not in the state S1 anymore. This is what the negation is doing. So when we add an activities, we are just moving over the automaton. While when we perform a delete, we do not move over the automaton as we have seen in the example, and we move only on the trace. And that's it. So as conclusion, we have explored some key problems in declarative process mining: log generation, conformance checking, and trace alignment, which are reasoning problems over event data. And we have seen also process discovery, which is about learning, about mining the data in order to find a model. So we have seen how in this case, learning is actually reduced to a combinatorial search and optimization problem as all the other problems. So there is not really a difference between learning and reasoning. They are all just combinatorial search and optimization problem. After that, we have seen how to solve those problems using automated reasoning. such as SAT solver and AI planners. And as a future work, one possibility is to consider other combinatorial search approach, such as local search. And so to learn and repair a process by starting with a model and then performing local perturbation until we find a model that satisfies us, that is compliant enough with the event data we have observed. And that's it.
Thank you, Francesco.
Yeah.
So James had a question, straightforward one. So what kind of event data people usually use for this kind of techniques?
Okay.
Right, in real life. What people want, what kind of models people train it on?
Basically, every information system has a log recording all the activities performed by all the human resources working on for the company, so that we have those strings representing how a process is performed. Here we have seen the pizza process.
For every time Francesco cuts out, it's eventually true that he returns.
Sending
Globally.
some product to clients.
Yeah.
So they all look like that. And then we can check the properties over the properties of those data.
Yeah, right. Is it scalable? It's like if there's a process that actually uses, right? There's another disconnection activity happened.
I think the connection is a bit unstable.
Right.
Well-
It's unstable, but eventually you come back each time. So yeah, this is used a lot in distributed systems, or you need processes with guarantees, like in the banking systems, I guess.
He's not back yet.
Ah.
5G switch.
Oh, he's
I heard only the word distributed system. And yeah, because you can have, in a certain way, you can perform a social network analysis to see which resource perform which activities and how the resources related to each other in terms of the task they do. So you can analyze also the organizational structure of the company. So it has actually a lot of application in industry and the business. It actually arises from information system engineering, about how to analyze the data collected by the information systems.
Right. It reminds me of the cause of discovery problems when people, instead of trying to derive some kind of formula or state automata, right, you derive some causal structure of your events so that you,
Yeah, this in a sense is a causal structure.
yeah, so it's like a machine learning when instead of you having like a linear log, you have some just data with some distribution, and you want to try to discover what kind of causal processes cause that particular distribution in your data. But here you have a linear structure instead, but right? But you can also use some kind of probabilistic.
Having different instances, we can see, for example, in one instance, we see add cheese before add tomato. In another instance, we see add tomato before add cheese. So we figure out that we can perform those permutation, and the only requirement to add ingredient is to have prepared the base before adding them, which is natural for us. So we can learn those kind of relation actually from the data. Before adding the ingredients, you need to prepare the base. And to prepare the base, before preparing the base, you need to buy all the ingredients. to start making the pizza.
So do you know, does it form like a, in some categorical terms, some monoidal category that if you have these parallel processes, which is like a monoidal product, do you know? It's like there's a some
I'm not sure about that.
string diagrammatic way of expressing all this kind of diagrams and processes.
Mm.
I may,
I'm not
okay.
familiar.
Oh, you should look into string diagrams in general, because process
Pardon?
theory.
Process theory.
Yeah, process theory with string diagrams. This is like more diagrammatic approach to it. So essentially, like in this example that you have, you're just composing a bunch of processes, which is one example of product. It's just like here you're composing horizontally, but usually you compose it vertically, and you also have the parallel product, which is usually a horizontal product, right? And then categorical forms is like a monoidal product, and your composition is like a like a composition in the category theory. So you can this whole thing forms a category, and you can loop around. You can also express some loops in the. Oh, by the way, is there some kind of way of looping in this process? There's no time closed time loop, right?
Actually, it's possible to loop. Yeah.
Yeah, impossible. Yeah, but the string diagrams, there's some loops in there because they called strings just because you can actually bend them and turn them back in time, so to speak.
Mhm.
It's very confusing because it's also called process theory, and you also refer to the processes.
Yeah, process mining. This one is cool, but yeah, I think they are kind of probably kind of related.
Yeah, I think the only difference is that loops.
Model. I'm reading from James. Yeah, basically, given those data, you can learn a model that someone else is using. This is basically model learning. If you have access to the data of a company, which is usually not the case, they are used for they are just internal data.
There's a packlet called Automata by Klaus Stuttner, and they talk about semi-groups.
Mm-hmm.
Now Nick is frozen.
Okay, yeah, it's automata. Seems to be.
Nick's back. You cut out.
This is a connection problem
Mm-hmm.
all over the.
Where, can you hear me?
Uh-huh.
Yeah, so the idea there is that you just monitor all of the API calls for some kind of external service. And then eventually you can maybe use a tool like this or technique like this to recreate an internal application that can completely replace that external proprietary system just by monitoring all the API calls. So there's kind of an interesting use case for this in industry at the moment.
So like reverse engineering, basically.
Yeah, reverse engineering a third-party service, and then using a technique like this to get, you won't catch every single edge case, but if you can get 95% reproducibility, and you can replace an entire proprietary service by an internal one that costs nothing, there's a huge demand for that kind of thing.
That's really interesting.
Yeah, this was fascinating. Thank you, Francesco.
Is it eventually gonna?
We don't know.
Yeah.
This is
And
right.
The trace has finally resolved. Thank you. Okay, so we're just saying thanks so much for joining us, Francesco, and appreciate your time showing us this interesting mathematics and kind of new technique.
Yeah, super
Thanks for
interesting.
inviting me.
Thank you for coming.
Bye bye.
All right.
Thanks,
Thank you all
Francesco.
for tuning in. We'll see you again next time.